PS3 test review for Learning Assessment 3. So this would be for lessons, and again, the book calls them lessons. I really refer to them as chapters, but it's lessons 6, 7, and 8. So the first thing we want to talk about, one of the things that we mentioned so far in these lessons is what makes things go sideways, or in other words, what makes things change directions. So, for example, if I have a merry-go-round here, we look at this merry-go-round, and again, it goes in a circle. So if a merry-go-round is moving at a constant speed, so I want to definitely make sure I understand this is at a constant speed. Is there any sideways force acting on it? And the obvious answer is yes, there has to be. If things are going in a circular pattern, and again, it's a constant speed, is there any sideways force acting on it? Yes. In order for things to change direction, there must be a sideways force. For example, when we were rolling the softball in class, the softball was rolling and you guys were supposed to push at it with your finger on the sides as it was rolling. And as that happens, as you pushed, it would start to go off to one side. So in order to get sideways motion, in order to get things to change direction, you must have sideways motion. Now, one of the other things you're going to have to be able to do on a test is you're going to have to draw a free body diagram. Now, a few of you are still getting confused between models and free body diagrams. This is the full model. This is everything. So if I ask for a free body diagram, and this should look familiar because we did this one in class. Here's ball A and ball E. So let's draw one for ball A. All we're doing is taking a look at the forces involved with ball A. We don't have to be concerned with this stuff over here because it doesn't impact ball A. So only the forces that affect ball A. So I'm going to make a circle just because it's a ball. So when I draw in the free body diagram, I've got the magnetic force. And again, it's a dashed line because it acts at a distance. Make sure you label what it is. Magnetic, I'm going to just say force acting on the ball. And did I draw that in right? Well, I could do it that way because I'm drawing this line right here, and it is taking it that way. If you wanted to draw it over here on the other side, you could do that. So why don't we change that? I think I like it better on the other side. But as long as it's going in the same direction, it really doesn't matter. So magnetic force. So I'm just going to look at this diagram. There's an arrow here. Okay, this is the contact force. Now I can draw it on the same side if I want, or I could draw this on the other side. So I can say this is a contact force with the magnet. Sorry about my writing. I'm trying to write and I can't see where my hand is because I'm writing on a tablet off to the side. So this is a contact force, so it's a solid line, and I show the direction. I'm just interpreting this diagram. So what we have here, we have another contact force. This is, according to this, I'll just say the rail. Sometimes, if you guys said table, because we did this on table, you could. I'm going to write rail. How about this? Contact force with the rail. So I have that, and then the only other thing I need is gravity pulling down, or the weight. So, and I'm going to label that the weight. Again, I'm sorry I'm getting everything crunched in here, but you get the general idea of where everything goes when we do this. So make sure you can interpret a diagram. So I might have you do ball A, I might have you do ball E, I might take another diagram. Now, one of the other things you have to be able to do with one of these diagrams on the test is you have to be able, if I erase all this, what you have to be able to do is you have to be able to interpret everything and make sure everything's right. One of the questions on a test is I'm going to give you a diagram like this, and you're going to have to look at it and say, okay, is this correct? Is this one correct? Is this one correct? Is this correct? And you're basically going to have to just evaluate it. and you're going to have to see if there's any mistakes. For example, if this was a solid line, you would say, oh, here's a mistake. It's a solid line. It should be a dashed line because it's a force that acts at a distance. Or maybe this one would be a dashed line, and you would say, nope, that's a contact force. It should be solid. Maybe things will be pointed in the wrong direction. So ultimately, you are going to have to be able to interpret one of these on the test. You're going to have to draw a free body diagram, and you're going to have to interpret these as far as seeing if all the arrows and everything is correct. One of the other things you're going to have to do is you're going to have to be able to answer basic questions about this. For example, I could ask you what vertical forces are interacting with ball E. And you would say, okay, the two vertical forces are the contact force between the rail and ball E and weight pulling down on it. I might ask you, why does ball A not move up and down? Why does it not move vertically? And you'd be able to say, well, these two must be balanced. Now you might look at this one and say, well, why is it longer? Well, it's longer because it's connecting with the earth here. And remember in our models, we drew them longer so that way it's connecting with ball A and the earth. It's not necessarily showing magnitude on this example anyway. Some might show magnitude. I might ask you why, or how about this right here? Remember the magnetic cannonball E went flying off? I might ask you, okay, what was the greater force? The magnetic force that acted at a distance or the contact force between D and E? And you would say, well, the contact force between D and E must have been greater. Why? Because the ball went flying off. If the magnetic force, the force that acted at a distance was greater, then ball E or ball, well, the ball might have shot off, but then it might have come right back because the magnet pulled it back. So you're going to have to answer basic questions that are similar to that. So again, being able to decipher this, be able to draw a free body diagram from it, to be able to evaluate all the arrows to make sure everything's correct is going to be huge on this next test. You're going to have questions that are similar to this. For example, two magnets are attracting each other. One magnet is big and strong, the other is small and weak. The big magnet attracts the small magnet with, well, no force at all. The same force with which the small magnet attracts the big magnet, a weaker force than which the small magnet attracts the big magnet, or a stronger force than which the small magnet attracts the big magnet. So again, what I would always suggest is go through, cross things off. For example, you know there's going to be a force involved. If it's on our planet Earth, there will be a force involved. So that's an obvious no-brainer. Got to get rid of. The same force with which the small magnet attracts the big magnet, a weaker force and a stronger force. Now I know this is a big magnet, but we talked about this in class. When I push on the wall pushes back with the same force. And that's definitely what applies here. Now we've got to be careful. Don't get confused with Newton's third law of motion, because Newton's third law of motion must work with his other laws of motion. So don't think that because the big magnet is larger, it's going to attract the small magnet more. It won't. It's going to be with the same force. Now that's not to say if there's a huge magnet here and a little magnet here, and we put say a ball bearing right in the middle, obviously the ball is going to go here. But then again, that's because it's a larger mass, not necessarily because when these two have an at a distance force, that doesn't necessarily mean one's going to be larger than the other. So we got to make sure we don't get confused with that. I'm showing you this picture right here because on the test, you're going to have to create a graph. Now, we created graphs with this, and this is what we made from it. Make sure you're able to do that. Or we took, in some of the homeworks, we took graphs and we had to answer questions. This is one where we had to answer questions. This was one of the homework ones. These we actually created in class. This one, and this one. So make sure you know how to create graphs. I'm not going to tell you exactly which one to create because then I won't know if you just copied it or if you really know how to interpret information. So this was the information that we used right here to get this graph. For this one, remember we used a pendulum and we used that picture to create this graph. So you're going to have to be able to do things like that. Here's another question. Analyze the figure and use it to answer questions. So we're going to have to be able to look at diagrams and be able to answer questions. And a lot of these questions basically are, well, they come from this chart. So if we remember, we filled this chart out in class. So make sure you study this chart and you know exactly what's going on here. So when the ball is on its way back up at point B, what forces are acting on it? Okay, so the ball got dribbled down and now it's coming back up. So it's at point B. So let's go through the options. There are no forces acting on the ball. Okay, no forces. I'm going to get rid of that right away because I know there's going to be forces on it, at least here on Earth. Both gravity and the force from the floor are acting on it. This is going to make me think a second. Forces from the floor. The ball's not on the floor. It already left the floor. So there should be no forces on the floor acting on it. It's not acting on it anymore. It already left the floor. Only gravity and air friction. This one sounds pretty good, but I am going to read the last one to make sure. Only the force from the floor. Nope. We already talked about it's not the floor anymore. So it's got to be this one right here. When I look at this one, you may look at this and say, oh, it's the same question, but let's read it. When the ball is on its way down at point A, what forces are acting on it? So now we're using this diagram here. So someone dribbled it. Now it's at point A. There are no forces acting on the ball. Again, cross it off. We know that there are forces acting on it. Both the pull of gravity and the force from Lisa's push are acting on it. Now, if we wanted the ball when it was here, yeah, I can see that. But when the ball's down here, Lisa's not pushing on the ball anymore. So Lisa's push does not apply. Only gravity and air friction are acting on the ball. That sounds pretty good. Let me read the last one. Only the force from Lisa's push is acting on the ball. Okay, we get Lisa's push again. We already said that's not good. So do you notice how I go through all 4 questions just to make sure that I'm not, jumping the gun and saying this is definitely the one before I read them all? That's a good thing to do on tests. And notice how I cross ones off as soon as I know they're not correct. That's another good strategy. So again, make sure we know all this information. So let's apply some of that information again. So a rocket in outer space traveling towards a far-off planet. An astronaut turns on the rocket's engines, which exert a force on a rocket. Now here, this is important. Assume there is no gravity or air resistance. While the engines are on, okay, so the engines are on, how will the rocket move? The rocket will move only while the engines are on. The rocket will move faster and faster as long as the engines are on. The rocket will move faster and faster until it reaches its maximum speed. The rockets will move at a constant speed. So here we got to think about this. We've got the engines moving. They're applying a force in this direction. So the rockets will only move while the engines are on. The rockets will move faster and faster. Now, if we're applying a force in the direction of the movement, if we go back to this way, so unbalanced forces acting against, nope, it's not against, we're going in the same direction. Unbalanced forces acting in the direction of which motion occurs, so it should be speeding up. So is that an option? The rocket will move faster and faster. Yep, right here it is. Okay, so you notice how we went back and I looked at the diagram. Now you're not going to have the diagram, but you need to study the diagram and know what's going on. So let's look at another example of outer space. Again, same topic. There is no gravity or air resistance. When the astronaut turns off, so now the astronaut turned off the engine. So before we had this push here from the rocket engines. Now what happened? There is no push anymore. So when we look at that, it will steadily slow down. So let's think about it. There is no push this way. So that's out. Now there is no air resistance or gravity. So there's nothing pushing it this way. So that's out. So if we go back to here, is there an unbalanced forces acting against it? No. Is there an unbalanced forces acting in the direction in which the motion occurs? No. So what must be happening? There's no unbalanced forces. So let's see if that's an option. It will steadily slow down. No, we already talked about. It's not slowing down because there's not a force that's opposed to the motion. It will steadily slow down because no forces. Nope, it's not slowing down. And now, no forces are acting on it. Well, one of the things that we have to talk about is without gravity and air resistance, a lot of times I'll say, well, there must be a force. There must be a force. Well, if you're in outer space, there may not be a force because we don't have the air resistance or gravity. How about this one? Or you might have some gravity from distant planets. So I should say that in there. So there's not absolutely no forces. So, but it doesn't necessarily apply here. It will continue moving with a constant speed. Okay. Because no forces are acting on it, it will continue moving with a constant speed because the force from the engines is still acting on it. Wait a minute. We cut the engines. We turned off the engines. So by reading, I know this is wrong, and this is the correct answer. So this is just a quick review for the next test that we're having. Again, what I would suggest you do is I suggest you watch the video. You study the video, you look at the video, you ask questions of your science teacher if you have any questions. Don't just watch the video to watch the video and to say, well, I watched the video, so now I'm going to do well. You do need to study, you do need to prepare. Now, ask lots of good questions, pay attention in class, and if you do that, you should do very well on this next test. So as always, if you have any questions, be sure to ask. Thanks. Bye.